Hey everyone, Mr. Glover here, just about to do our next set of notes. So up until this point, we have talked about several different strategies to solve counting problems. We've got things like the counting principle. We have things like the permutation formula. We have the combination formula, and we've also got Venn diagrams, tree diagrams, and outcome tables. So the idea today is about kind of solving an arranged or solving a selection of different problems where we've got to make the choice, which technique do we use to solve it. So far, there's four different types of counting problem, or four sort of categories. There's selection where the order matters, and if the order matters, that tells me that it's a permutation question. An example of a permutation problem would be something like the number of words made by or made with the letters A, B, C, or D. Selection where order doesn't matter. That's a combination. So an example of this could be like the number of different combinations of Smarties. Doesn't really matter what order you put the Smarties in the bag. It's about how many reds, how many blues, how many purples, etc. Type 3 would be problems where multiple choices are made at once. And these are going to be fundamental counting problems. The key to this one, and I'm going to highlight it, is at once, because they have to be happening simultaneously. An example of this would be buying a bike with 7 different options. So you have to think about like how many different handlebar combinations do you have? How many different pedals do you have? How many different tires do you have? And then the fourth kind is problems happening one at a time. And these are the OR problems. These are the ones that I'm just going to call them OR problems. So it's not about doing a bunch of things at once and how many ways can it be done. It's about we're going to do one thing and how many ways can we do it. It's a minor difference, but the difference here is that the fundamental counting principle doesn't apply. And if the fundamental counting principle doesn't apply, the only way we can do this is using set theory. An example of this would be something like the number of ways to draw a red card, and perhaps or a 7. And we'll maybe look at this question a little later. So when solving counting problems, ask yourself a couple of questions. Question 1, can I use the fundamental counting principle? And that's, is this an OR question or an AND question? If you can use it, list out each choice made and draw like a line for each choice, then multiply by the options for each of them. If no, you may need to use set theory, and that's where you draw the Venn diagrams. That's where you draw a diagram or Venn diagram, and you'd have to add the choices on one side and the choices on the other side and subtract the intersect. Does the order matter? If yes, use permutations. If no, combinations are what you're going to need to use. So these two are almost the same, but it's a difference in formula. We use a combination versus a permutation. So let's try a question. T-shirts are available in 5 sizes, 3 colors, and have 4 different logos. How many different t-shirts are available to buy? So this is a question where the fundamental counting principle does apply because we are making multiple choices simultaneously. We are making a choice on size and color and logo. So because of that, the fundamental counting principle applies. We list out a blank for each of our choices. So we'll have one blank for size. We'll have one blank for color. And we'll have one blank for logo. And then we just write in the number of choices for each of these. So we've got 5 options for size. we have 3 options for color, and you'll have 4 options for logo. Sorry if you can hear the sound in the background. We've got people playing out in the sunshine and dogs barking, so just have to bear with me. So we're going to finish this problem off. We have to just take our choices and we just multiply how many options we have for each choice. There's 5 sizes times 3 colors times 4 logos. That will leave us with a total of 60 possible t-shirts. And we can then go ahead and circle our answer. All right, let's try another question. Oops. A teacher wants to pick 2 boys and 2 girls to be hall monitors. His class has 10 boys and 13 girls. How many different combinations of students could he pick? So again, we've got to ask ourselves, does the fundamental counting principle apply? And technically, yes, the fundamental counting principle does apply, but there's a better way to do this, and that's using permutations, or sorry, using combinations. It doesn't matter whether we pick 1 boy first or 1 girl first, or 1 boy second or 1 girl second. It's just that they've gotten chosen to be a hall monitor. So order doesn't matter. Order doesn't matter. And what that means is that this is a combination problem. By the way, you can't just use, if you read the word combination, that's not necessarily going to mean you've got to use a combination. A combination to a lock matters if it's 1, 2, 3 or 3, 1, 2. So don't get too hung up on that word. But we're using combinations here. We're basically going to have to break this into categories. We're going to have to break this into 2 boys. And we can put a box around that, times the number of ways that we can select 2 girls. And now we've got 10 boys and 13 girls. So to pick the boys, we would go 10, choose 2. We're picking 2 from a population of 10. And to pick 2 girls, we have 13 to pick from. 13, choose 2 is the number of ways to pick the girls. 10, choose 2 works out to 45 ways to pick 2 boys, and 13 choose 2 works out to 78 ways to pick 2 girls. If we multiply those together, that gives us 3,510 combinations. And there we go. So essentially, first question, ask yourself, can the fundamental counting principle be used? If the answer is no, immediately you've got to use Venn diagrams. The next question is, does the order matter? If no, use a combination. If yes, use a permutation. All right, let's try another one. So example, the same teacher as above needs to pick 3 students to fill roles in his classroom. He needs 1 marker. So 1 marker. He needs 1 hall monitor and 1 detention supervisor. How many ways could he pick students for these 3 positions? All right, so this one's a little bit of a different problem. Question 1, fundamental counting principle, does it apply? Technically, yes. We're choosing 3 people, I guess, simultaneously. We're not choosing a marker or a hall monitor or a supervisor. So fundamental counting principle technically applies, but the better way to do this is to do this using permutations. So the order does matter. Order matters, which tells me that this is a permutation question. The reason the order matters is if I pick Bob first, Bob might be my marker. If I pick Johnny first, Johnny might be the marker. But if I pick Johnny, then Bob, well, now Bob's the hall monitor. So the order you pick them in gives them different roles. So it's a permutation. 1 marker, 1 hall monitor, 1 detention supervisor. So essentially, it doesn't matter if we're picking a boy or a girl here. We're just picking 3 students. So we've got a population n equals 3. And now you could think about this as creating a list of names. The first person on the list gets marker, second person on the list gets hall monitor, third person gets supervisor. So we're basically picking 3-person permutations out of the class. So n equals, n equals 23, sorry, that's how many students are in the class. R equals 3, because we're choosing 3 people. So number of ways to pick them, 23 permutation 3. That equals 10,626 different ways to pick. And I'm just doing these on my calculator. You can do them by hand if you want, but at this point, use your calculator. It'll save you a bit of time. All right, another question. So Brooke is picking cards from a deck at random. How many different ways could she pick a black card or a 7? So this question is a little bit different. The one thing that really stands out like a sore thumb is the fact that I've written the word or, and it's capitalized. The or tells me the fundamental counting principle does not apply. So the FCP doesn't apply. So what that tells me is we've got to use set theory, which means we've got to use the Venn diagrams. So what we're going to do is we're going to create a Venn diagram for all black cards and a Venn diagram, or 1/2 for 7s, and we're going to see what falls in the middle. So let's draw our Venn diagram first. So the one on the left will be black cards. The one on the right will be 7s. And we're just going to write the numbers. We're not going to actually list every single one. As far as black cards go, there's 13 of each suit, and there's 2 suits, so there's 26 cards. As far as 7s go, you've got 1 7 for each suit. So in the deck of 52, you're going to have 4 7s. But then in the middle, we've got to count the ones that are double counted. So we have 4 7s in our deck, but 2 of them are black cards. 2 of them are, or one of them is the 7 of spades, one of them is the 7 of clubs. So we have 2 black 7s. And those kind of fall in the middle. So we want to go and use set theory to solve this. It's going to be kind of an ugly formula, but the number n, so number of ways, is going to equal 26 plus 4. That's the union of those 2 sets. So it's black union 7. 26 plus 4. But then we have to subtract the ones that are being double counted minus 2. This is going to work out to 28 ways. And I mean, if you think about it, it makes sense. We've got the possibility of picking any of the black cards. We've got those. Or a 7, the other 2 7s available are the 7 hearts and 7 of diamonds. 26 plus 2 gets me to 28. The key here is immediately recognizing that it's an or question and not an and question. If it was an and question, we would have to split this up and use combinations. Number of ways to pick 1 black card would be 26, choose 1. Number of ways to pick 7s would have been 4, choose 1, and then you would have had to multiply. All right, a couple more questions here. Chastity's picking 2 cards from a deck at the same time. How many ways could she pick 1 black card and a 7? So if we're picking both a black card as well as a 7, we just have to use the fundamental counting principle. Fundamental counting principle applies. We've got 26 black cards. And we have 4 7s. Oh, actually, we need to be a little bit careful here. Number of ways to pick a black card and a 7. We just have to make sure that if we were to pick a 7 of out of the black cards, like a black 7, we would only have the other suits available for our 7. But this will be all right. This will work. So we write a blank for the black cards. We write a blank for the 7s. We have 26 ways to pick a black card, and we have 4 7s. If we go and multiply those together, 26 times 4 gets me. Oh, never mind. This is where we're running into problems. We don't actually have 26 black cards. We've only got 24 of them because 2 of them are 7s. So because we've got 24 of them, we're essentially not allowing one of our black cards to be a 7. We're choosing all the black cards that are not 7s. So maybe we should write this up top. 26 black cards, but 24 that are not 7. With 4 7s. 24 black cards times the 4 7s gives us 96 ways. Sorry about that. That's not probably a little bit hard to follow. So I'll kind of rehash this question. We list out the number of black cards, but we can't double count the 7s, so we have to just remove them. Think about it as being black cards that aren't 7. So maybe black, not 7. There's 24 of those. We multiply by the number of 7s, which is 4. That gets us 96 possible combinations. All right, how many different 3-letter words can be made from the letters in the word Calgary? And I'm going to kind of provide a little bit more criteria here in that there's no repetition of letters. Okay, if there were a repetition available, this would be a little bit trickier because we would be doing a portion of a word with repeated elements, and we would have to break it up into cases. And essentially, we're going to be stuck writing out every 3-letter word. If we can't repeat the letters, this problem becomes quite a bit easier. So we want 3-letter words made from the letters of this word, but since we cannot repeat the letters, we don't really have to worry about having 2 A's. We can just break this word down into the letters C, A, L, G, R, and Y. We're skipping the second A because it's not a distinct letter. If we do that, 1, 2, 3, 4, 5, 6 leaves us with 6 letters. It's not 7 because one of them was a repeated element. So if we have 6 letters and we want to make 3-lettered words, does the order matter? If we're making a word, the word cat is different from tack. So yes, the order matters. Order matters. Tells me that this is a permutation. So if we're picking out of 6 letters, we're picking 3-letter words. We're essentially just doing 6 permutation 3. 6 permutation 3 is 120 words. Now we got to be careful. If we had chosen 7, because there's 7 letters in the word Calgary, we're going to get a lot more than 120 words. But because we recognize that there's no repetition, we did eliminate one of those letters. We're actually only working with 6 different letters. It's 6 permutation 3. All right, one more question. How many poker hands have 2 spades and 3 clubs? Does the fundamental counting principle apply? Yeah, it's an and problem. We're not dealing with or. Second question, does the order matter? Poker hands can be reordered however you see fit. So the order doesn't matter. Order doesn't matter. And what that tells me is that this is a combination, not a permutation. So when we're dealing with number of ways to get 2 spades and 3 clubs, break it up into 2 spades and 3 clubs. 2 spades times 3 clubs. We have 13 of every suit. So n is going to be 13 for both of these, and r is going to be the number we're picking. So if we're picking 2 spades, 13 choose 2 is the number of ways to pick them. If we're picking 3 clubs, 13 choose 3 will get us the number of ways to pick them. 13 choose 2 is 78, and 13 choose 3 is 286. If we multiply those together, we have 22,308 possible hands. And there we go. So essentially, whenever you're solving these problems, now that we're not locked into a chapter all on combinations or all on permutations, we've got to do a bit of this legwork before we actually go and solve the problem. We're going to have to do ask some questions. We're going to have to ask, first of all, does the fundamental counting principle apply? Are we making multiple choices at once? If so, yes, it applies. If not, if it's an OR question, we've got to use set theory. Second question is, does the order matter? Oftentimes, if we're dealing with words, the order will always matter. If you're dealing with cards, the order often doesn't matter. But you're going to have to figure that out for yourself. Once you've figured that out, you've now got a strategy: fundamental counting principle, set theory, permutations or combinations, and then in some weird circumstances, we might have to actually list them all out using like a tree diagram or something. And then that's pretty much it. So this is just the chapter that joins all of the units that we've done so far together. I've got some questions for you. Questions 1 to 3, 5, 6, 8, and 9. It used to be 1 to 6, but question 4 is kind of weird the way that it's worded, so I decided to remove it. This will be your homework for today, and it's out of your workbook, not the textbook. So I'll end the video here. I hope everybody has a great rest of the day, and I will see you all tomorrow in our Zoom chat. Take care. Bye for now.